Welcome everyone to another seminar on mathematics and high energy physics at Physics Latam. Today we are excited to have Alessandro Giacchetto. He did his PhD in Bonn University under the supervision of Gaetan Borot and worked at the Max Planck Institute for Mathematics. Currently he is postdoc at the Institute of Theoretical Physics at Saclay, Paris, as part of the Renew Quantum project led by Andersen, Einar, Maxime Constantich, and Marco Marinho. He is interested in the interactions between geometry and theoretical physics, in particular, the enumerative geometry of modular spaces of Kerr and Gromov-Witten theory. Also interested in topological recursion, integrable systems, and matrix model. Thank you very much for accepting this invitation.
Thank you for inviting me. All right, so the goal of today's talk is essentially to explain this picture, which is a pictorial way of representing topological recursion. And so in a nutshell, topological recursion, you can think of it as a kind of black box that takes an input and spits out an output. And so the input will be something called a spectral curve, which will be essentially a Riemann surface, sigma, with some extra data that I will explain later on. And the input are called correlators. They are denoted with this omega g n's associated to the spectral curve S. And they are labeled by two integers g and n. And these objects here will be n forms on the nth product of the Riemann surface sigma. And they, in many cases, they will either have a physics interpretation or a geometric interpretation. With the language coming from physics, well, in the specific case of n equal to 0, this omega g0 are just complex numbers. They are sometimes denoted with an FG and are called free energies. And so the goal of today is to explain exactly what is this concept of spectral curve, what is this topological recursion formula, and what you can do with these outputs. And before asking how, you should ask why. And the main point about topological recursion is that, well, first of all, it has many different applications. Most notably, well, random matrix theory. This is how topological recursion was developed. But also many different things in geometry and physics, like volumes of moduli spaces, mirror symmetry, Gromov-Witten invariants, or in general topological string applications, Hurwitz numbers, and so on and so forth. We will see some examples later. And one other feature of topological recursion is that it satisfies many interesting properties, like Virasoro constraints, integrability, Seiberg-Witten geometry, and so on. So the main point is that when you are trying to compute something and you show that this is computed by topological recursion, you can then have all these properties for free, just knowing that the problem itself is solved by topological recursion. Okay, so this is what you somehow have to take home. Let me start explaining this topological recursion formalism, starting from its origin, which is random matrix theory. So I guess one week ago you saw you had a seminar on random matrix theory. I will just recall a bit the history just to be on the same page. Random matrix theory somehow, one of the first breakthrough, it's from the 50s when Wigner was trying to describe the energy spectrum of heavy nuclei, and he managed to do that using random matrix theory, and from that point on, this business of random matrices, it was used in to describe systems with complicated Hamiltonians and complicated length spectrum. Another breakthrough in the theory of random matrices was by 't Hooft in the 70s, when he was studying quantum chromodynamics, and he realized that, well, if you imagine to have a theory of quantum chromodynamics and you take the number of colorings to infinity, a lot of simplifications occur. And the main point is that in this case, when you try to do Feynman diagram extensions, you can realize this expansion as a sum over certain graphs drawn on surfaces. And the main point here is that essentially the propagators in this kind of theory, it's indexed by indices in your matrices. So the interaction will look something like this. And this is a graph that you can draw on a surface, right? So the Feynman diagrams in this kind of theory is not just a graph; it's a graph on surface. And we will see later how this is actually very important in the theory of topological recursion. And again, in the 80s and later on in the 90s, Brezan, Itkinson, and Zuber, they managed to connect this random matrix theory to topological or to 2D quantum gravity. Again, thanks to this idea of matrix models as a way of essentially triangulating a surface, and a systematic approach to this large N expansion in matrix models was developed in the early 2000s by Chekhov, and Dorantan with this theory of topological recursion. So this is a bit the history, but so let me be a bit more concrete. So the setup I want to consider in this case is the following. You take Hn to be the set of n times m Hermitian matrices, and you consider a measure d mu, which is the following. It's the exponential of -1 over h bar trace of a certain potential that I will call V, times dm, which is the standard Lebesgue measure that it's UN invariant on the space of Hermitian matrices. And out of these two gadgets, you can construct a partition function, Z, which is just the integral of this measure on the space of Hermitian matrices. Okay, and when you have something like this, there are some natural quantities that you can try to compute. So these are observables of this form. I will denote them with this bracket F, or so this vacuum, these expectation values are just the integral of F times the measure normalized by this partition function. And so the most natural observables that you can think of are, well, they have to be, conjugation invariant. So the most natural one that you can think of is probably the trace, right? The function trace of M, it's the most natural thing you can try to compute here. And more generally, you can try to compute trace of products of powers of M. And a convenient way to bundle these observables together is to take this generating series. And so when you do that, you can write it as the trace of 1 over x minus m. So this is known as the resolvent. At this point, x is just a formal variable, but it's a way to bundle together all these natural quantities that you might try to compute. Another conjugation invariant quantity that you can try and compute is the determinant, or more generally the characteristic polynomial. And well, for a certain reason, in this case, it's more convenient to rewrite this as a trace again. So and in order to do so, you can write the determinant as the exponential of the trace of the log. And with a bit of manipulation, you can write, the log as the integral of 1 over x minus m in this case. And if you expand the exponential, you will end up with the, if you expand the exponential and you take the expectation value, this is by definition essentially the same as taking the exponential of something known as the cumulants. So if you don't know what the cumulants are, it's not important. This is essentially the definition. You can just think of them as a different way of packaging expectation values of products. It's just more convenient from a computational point of view. But at the end of the day, it's just a different way of repackaging expectation values of products. And the upshot here is that if you want to compute the expectation value of the characteristic polynomial, this is the same as computing all the cumulants. And another quantity that you might try to compute is something called the spectral density, which is just essentially the expectation value of the position of the eigenvalues. And you can do so by essentially integrating the sum over n of Dirac deltas located at the eigenvalues. But again, this is essentially the same thing as the resolvent, because you can write a Dirac delta in this way, where here you again have x minus lambda, which is exactly what appears here. So this is to say that for most of the natural quantities that you might try to compute, the only thing that you need to understand are these cumulants, and well, the cumulant here when n is equal to 1 is the same thing as the result. So because cumulants are so important, let me give a name to this. So this I will denote with this Wn of x1 up to xn, this cumulant. These are called endpoint correlators, and again, when n is equal to 1, the cumulant here doesn't play any role, and you get the resultant. Okay. So, okay, the main question now is, how do we compute this endpoint correlators, right? And here we can try to follow Etoff and say, okay, let's try to compute this endpoint correlators in the large n limit, when, let's say, n times h bar is fixed to be a constant. This is sometimes called the Etoff parameter. And I recall here n is the size of the matrices, and h bar is this parameter that appears in the potential here, right? And so what you can prove is that under some assumptions on the shape of the potential, for example, if the potential is polynomial or even something more general, you can prove that both the partition function and the endpoint correlators, they have an h bar expansion, or if you want, because of this equality here, 1 over n expansion. The exponents that appear here, they actually have something to do with this Feynman diagram expansion. And because of what I said at the beginning, that the Feynman diagrams are something more like graphs drawn on surfaces, the exponents here will actually have a geometric interpretation in terms of the geometry of the surface where these graphs will live. And this is essentially due to the Euler characteristic formula, because you can collect powers of h bar with something like the number of vertices minus the number of edges plus the number of faces, which gives this 2 times the genus of the surface minus 2. So because of this, these expansions here are called sometimes topological expansions. Okay, but the upshot here is that we want to compute all the partition function and these correlators, and in this large n limit, we end up with just a bunch of complex numbers and a bunch of functions of x1, xn labeled by this GNN. And again, it's the problem is still the same. How do we compute this? And what Einar and collaborators understood in the early 2000s is that all these WGNs, they can compute it by a universal formula that it's recursive, and it only depends on omega 01. So to be more precise, so first of all, what is this omega 01? If you remember W1, it's the resolvent, right? So it's this quantity here. And because of this, it has an H bar expansion. So it's something like 1 over H bar, omega 01 plus higher order terms. And I also said that this resolvent is more or less the spectral density. So this omega 01 is, well, it's the leading term of the resolvent, which is essentially the same thing as the leading order, the leading term of the spectral density. Another comment is that why is this formula recursive? Well, the point is that it's recursive in 2G minus 2 plus n. This, let's say, Euler characteristic that you can compute out of this indices GNN, which in principle they have nothing to do with actual surfaces, right? N is the number of products of that you get in the resolvent, and G is just labeling the H bar expansion. And for those of you who know something about loop equations, well, this formula here, it comes from a systematic approach to solving loop equations. I will not say anything more about this, but the origin of this topological recursion formula, it's a way of solving loop equations. And so let me just give you an example of this. So the easiest possible potential that you can think of is the Gaussian potential. And so this model is called the GUE, it's the Gaussian unitary ensemble. And in this specific case, when you can compute the leading term of the spectral density explicitly, and it's something like this, which is just a circle, which you can clearly see from this numerical simulation, right? So this is the spectral density, so the location of the eigenvalues, and when n is very large, you can see that they follow a semicircle. So this is known as the Wigner semicircle loop. And so this curve here is what is known as the spectral curve in the case of GUE. But because of what I said here, essentially this spectral curve, this omega 01, is the initial data for computing all these omega GNs. And the fact that this is related to the spectral density, it's the origin of the name spectral curve. And if you want to have fun with simulations like this, you can go to the website of Bertrand. He has a simulator like this that it's interactive. You can change and you can change the number of samples of eigenvalues. You can do it for GUE, GOE, and some other cases. Okay, so so far, I didn't tell you what is this topological recursion formula. I will postpone this for a bit still. But if you want, the main point of the work of Bertrand and collaborators is that they managed to find this universal formula for in relation to random matrix theory. But then in 2007, with Nicolas Ranton, they managed to somehow detach topological recursion from the theory of matrix models. And this was somehow the first main achievement, because it led to many applications that went just outside matrix models, and as we will see now. So before actually telling you something about the actual topological recursion formula, I want to jump ahead to another application. And I want to describe a bit better what is this topological recursion formula for the case of JT gravity. So JT gravity is a very old theory of 2D gravity, but in the last, let's say, 8 years, there was a kind of resurgence of this theory, starting from an observation of Kitaev from 2015. Kitaev was studying a certain quantum mechanical model known as the SYK model. And he noticed that this model has many features that you can see in black holes. And when you see something like this, where on the one hand you have quantum mechanics and on the other hand you have gravity, this is really exciting because it's something like ADS-CFT, some kind of holography correspondence. So people got really excited and they started studying this SYK model more and more. And first of all, people understood that this, let's say, gravitational dual to the SYK model, it's this JT gravity that was actually known since the 80s. But also people understood that this SYK model, it behaves like a matrix model. And it behaves like a matrix model in the specific with a very specific spectral density, which is this one here. And so people got excited because they thought, well, maybe we can try to apply matrix model techniques to JT gravity and try to study JT gravity with these more powerful techniques from matrix models. And just to show you how close this SYK model is to a matrix model, here it's a simulation taken from this paper of Colta. And on the left-hand side here, you have a simulation related to the GUE model. What it's plotted here, it's not so important. It's something called the spectral form factor. And on the other hand, you have something coming from the SYK model. Here, I should have said this before. This SYK model, it's a model which has something to do with fermions, and here this NM is the number of fermions. So the number of fermions in this model, it's what replaces the dimension of the matrices in the matrix model case. So in this sense, the SYK model behaves like a matrix model when you send the number of fermions to infinity. Okay, so but let me describe a bit more this JT gravity. And JT gravity can be described by an action which depends on two objects, G and phi, where G is a Riemannian metric on a 2D manifold. JT is a 2D gravity theory, and phi it's a scalar field called the dilaton field. And the action it's something like this. There's let's say a topological term, which is the Euler characteristic of your manifold times S0, which is, you can think of it as a coupling constant. In relation to black holes, it's something like the entropy. And if you think about it in terms of gravity, it's more like 1 over the gravitational constant. And then there are more terms. The main one I want to focus on is this one, where here you have well, the square root of the metric, the dilaton field, and then you have r+2, where r is the scalar curvature of the metric. And then you have some boundary terms that are not so important. But the main point here is that when you try to compute the Euler equations associated to this action, you immediately realize that this dilaton field implies that the scalar curvature has to be equal to -2, which means that the metric here is a metric of constant scalar curvature, that it's negative, and this is a hyperbolic metric, which is really nice because, well, this essentially means that when you try to compute the path integral associated to this JT gravity, you will end up with computations that involves integrals over the space of hyperbolic matrices. So let me give you an example here. So let's say you want to compute a very specific correlation function in this theory. It doesn't matter that much what this is, but the point is that, well, imagine you try to compute this as an expansion in e to the minus s0. So you treat this e to the minus s0 as a coupling constant. And what you will find is a topological expansion where this coefficients here, they have a very geometric interpretation, and they involves, as I said here, integrals over the space of hyperbolic matrices. And more specifically, they have a structure like this. They are essentially an integral transform of a product of two terms, something called a hyperbolic trumpet, and something else, which is something known as the Weil-Petersson volumes. So what are these two? So the hyperbolic trumpet, it's not so important. It's a very very explicit factor, which doesn't matter that much. The important part is this VGN. So these are known as the Weil-Petersson volumes, and they are the volumes of a certain moduli space. And this moduli space is the moduli space parameterizing hyperbolic metrics on surfaces of genus G with n boundaries of fixed length B1 up to Bn. So, which means that in this genus expansion, the G term it's essentially given by these volumes, which parameterizes hyperbolic metrics on surfaces of that same genus, with some boundary conditions that are essentially given here. And this is in line with what I said here. So this JT gravity involves its path integral involves an integral over the space of hyperbolic matrices, and in this specific case, this integral it's realized here as the volumes of this moduli space. So it's an integral over the moduli space of hyperbolic matrices of a certain volume form known as the Weil-Petersson form. And so the upshot here is that if you are trying to compute this correlation function in JT gravity, well, here everything is known except for these volumes. And well, here again, it's just a pictorial way of representing that formula. But the main point is that, well, these orange trumpets are very explicit. The only thing that it's not understood in this formula is this red part, which is these volumes. And as I said before, this JT gravity, it's in some sense dual to a matrix model. So you would expect this VGN, these volumes, to be computable using topological recursion. And this is indeed the case. So to connect it to topological recursion, I have to introduce yet another quantity. So I will introduce this WGN, which are just the Laplace transform of the volumes. So here, I'm sorry, there are many quantities. They all contain the same information. So you have this zeta, which are just the expansion of this correlation function. These are natural in the context of JT gravity, but this contains the same information as these volumes, which are very natural in the geometric context. but then I'm taking the Laplace transform of these volumes, which are more natural from the topological recursion point of view. But you should agree that this WGN, these VGNs, and this ZGN, they all contain the same information. So as soon as I tell you how to compute one of these three quantities, you will be able to compute all of them. And now I can finally tell you what is this topological recursion formula for the specific case of Bell-Peterson volumes or JT gravity correlations. And in this case, you will see how this pictorial way of representing topological recursion, it's not just pictorial, is literally what it's happening. And so this formula here, it goes as follows. So imagine you want to try to compute WGN, which again is the Laplace transform of the volume of hyperbolic, of the moduli space of hyperbolic matrix on a surface of genus G with n boundaries. And you can do so by introducing let's say a dummy variable, and you will then in the end take a residue when this dummy variable z goes to 0. And what you will do, it's, well, introduce a kernel, something that I will call a kernel, which is this expression here, which, as you can see, depends on two variables. It depends on z1 and the dummy variable z. And what you have to do is to take the residue when you multiply this kernel to two types of terms. The first term is this guy here. So let me analyze a bit more what is happening with the picture. So essentially, you can think of this kernel as something associated to this pair of pens. And as I said, this term, it depends on two variables. But you can actually think of it as depending on three variables. You have Z1, which is the first variable, the first boundary here. And then these other two boundaries attached to them, you essentially have the variable z and the variable minus z. And what you have to do here is, let's say, glue with this residue this yellow pair of pens to the correlator WG minus 1 and plus 1. And as you can see here, you can associate this guy as to an object like this, which is exactly what you would obtain when trying to remove a pair of pens from a surface of genus G with n mark points in such a way that the corresponding surface it's still connected. And if you do so in this kind of picture, you will see that you will end up with something of genus G minus 1, because one genus is contained here, and n plus 1 boundary components, which are these Z2 up to Zn that you didn't touch. And then you have two more boundary components, which are these two here. And attached to them, you have this variable z and minus z. But when you try to remove a pair of pens from a surface, you will also have, let's say, a disconnected case. And when you have something like this, you essentially have to sum up over all possible ways of distributing the genus and distributing these boundary components. So here you have a big sum over all possible ways of splitting G as G1 plus G2, and the wave on the ways of splitting Z2 up to Zn into two disjoint subsets, I1 and I2. And what you have to do here is multiply these correlators, where you have on the first one genus G1 and boundary components labeled by this first set I1 and a variable z here. So again, here you can think of it as having z and minus z here. And then a second correlators of genus G2, boundary components labeled by I2 and minus z, right? Okay, so this this is the topological recursion formula for the specific case of Weil-Peterson volumes or JT gravity. And there is still something that I didn't explain, which is this no 0, 1. So in this formula here, you are not allowed to take G1 and sorry, one of this G and one of this I1 or I2 in such a way that you will end up with a topology 0, 1 here. And this is not allowed because you can see that here, if you try to glue a disk, the resulting surface here will have the same genus and the same number of boundary components as the first one. So if you don't remove the 0, 1 case, you will not end up with a recursion. So again, just to be more clear, this no 0, 1, it means that you cannot have Gi and I equal to 0. Sorry, to 0 and the empty subset. Because if you have the empty subset here plus the one that comes from this formula, you will end up with the 0, 1. And so at the end of the day, this will be a recursion formula, and the only thing that I didn't specify is the 0, 2 case, which is given by hand by this formula here. And the reason why this was not specified before is, well, if I go up here, essentially this moduli space is only defined when you take 2G minus 2 plus n positive. This is because if you drop this condition, then you cannot find a hyperbolic metric on a surface with this Euler characteristic with 2G minus 2 plus n that it's 0 or negative. So there's no such thing as volumes of the moduli space of hyperbolic metrics if this condition is not satisfied. So the 0, 2 case, you have to specify it by hand, essentially. Well, the last thing I wanted to say is that this formula was proved by Enar and Dorantan as by taking essentially the Laplace transform of a formula by Mirzahani that proved this kind of formula from geometry using hyperbolic geometry. And in this specific case, this pictorial way of writing the formula is actually the correct way of imagining it, because in this specific case, this drawing is essentially what is happening in the proof of Mirzahani's. She managed to prove a formula like this by actually cutting out hyperbolic pairs of pens from an initial surface of genus G with n boundary components. Okay, so well, this is the main formula for this JT gravity or Weil-Peterson geometry. Let me maybe try to compute it in a specific example so that we can understand what's going on. So let's try to compute the 1, 1 case. So we want to compute W1, 1 of Z1. And so what we have to do, it's well, here I just copied this residue. And well, here to be more precise with this formula, well, you cannot really compute residues of functions. The correct way to do this is to compute residues of differential forms. This is because residues are just integrals, right? So and you have to integrate a one form, not a function. And this will, I mean, in this specific case, it's not so important because we are on C, but on general Riemann surfaces, this is crucial. So first of all, let me put a dx here, sorry, a dz here, which is more important. And so if you want to compute W11, well, this part is always the same, no matter what G and N is. And then you have to understand what to insert here. So in the 1-1 case here, you will end up with a W02 evaluated at Z minus Z, and here you have nothing. So this term here corresponds to this one. And then in the 1-1 case, this huge sum will actually be empty, because if you take 1-1, you can see that there is no choice of G1, G2, and splitting I1, I2, so that this condition is satisfied. So this term here will just drop because the sum is empty. So in this 1-1 case, you will only have this term here, and W02 is given by this formula. So when you set Z equal to minus Z, this will just be 2Z, right? So you only have to compute this residue, and I mean, I'm sure that now you would be able to go on by yourself, but let's try to see together what we can do to compute this. So first of all, you can expand in Z this term here, and this will give you this term here. And you can also expand the sign, so you get this 2 pi Z minus 1 over C 6 2 pi Z Z cubed, and so on. And so here I just copied this term, and I collected some the Z1 here and some constants, and this term here is essentially the expansion of 1 over sine. And so written like this, now it's easy to understand what's the residue. Here you have a Z cubed, so to get a non-trivial residue, you can either take this, which gives a Z squared, and a 1 here, so this will give this 1 over Z1 cube squared, or you can take the 1 here and this 2 pi squared over 3 Z squared, and this will give you this term here. So the final result after this residue computation is this simple rational function of Z1. But the point I'm trying to make here is that this is a very let's say simple type of computation that, you know, it gets more and more difficult the more GNN you have, but it's a recursive formula, so you can just code it on your favorite software, and as soon as you know what's the kernel here, you can just run this recursion and compute as many WGNs as you want. Okay, and well, to sum up, this formula here, it gives an answer to you know, the computation of these correlation functions in JT gravity, or if you want a way of computing recursively this these Weil-Peterson volumes. And the reason you should expect topological recursion to hold in this case is, well, first of all, it's because of Mirzakhani's recursion, right? In this case, this recursion is literally it comes from removing pairs of pens from hyperbolic surfaces. But in the context of JT gravity, you can also expect this because of this this duality between JT, this SYK model, and the fact that there are matrix models underneath that, and we know that matrix models in the large N expansion, they are solved by topological recursion. But as I said, this is just one specific example of topological recursion. So how do you write this in a more general setting? And so here I will try to essentially repeat what Einar and Dorantan did back in 2007. Here I will basically do this computation based only on this JT recursion formula. They had many more examples coming from matrix models. So some of the things that I will do now, they might be a bit random, but they had many more examples from which they based this generalization. And so now what I will try to do now is to make some observations, and I will try to modify this formula in such a way that it will not depend on specific ingredients coming from this hyperbolic geometric set. And so the first observation here is that, well, essentially these WGNs are not really the fundamental objects, because they do not transform well when you change these variables z. The way they transform is more like differential forms. So the basic object to consider are actually these omega GNs, which are these WGNs multiplied by dz1 up to dzn. And so when I do this on this formula here, so if I multiply by dz1 dzn, on the left-hand side, I will have this omega gn. And if I insist on trying to have this omega gns on this side, well, first of all, here you don't have dz1, so I have to, let's say, put it here. But here I will also have a dz and a d of minus z, right? So I put it there, so I have to remove it. So it's actually on both of this. So let me actually put it here. So we'll have a 1 over dz and d of minus z. And so this minus sign will just cancel with that. And I have a dz that cancels with this. Okay, so at the end of the day, what I end up with, it's something like this. And now we only have these differential forms. And if I do this for, let's say, for the 0 to k's, I will have something like this. And here I have dz1, dz2. Okay. And the second observation is the following. So let's take this omega 0, 2 here, and let's perform this operation here. So here I'm taking the second variable, and I'm integrating it from minus z to z, while keeping the first variable frozen. So because the first variable is frozen, I have this dz here. And then I have to integrate what it's left from, let's say, in z. Sorry, here there's a typo. I have to integrate it in the variable z prime from minus z to z. And so when you do this, you will have something like this. So it's dz1 divided by 2. And when I perform this integral, I get something like z1 minus z minus 1 over z1 plus z. And this whole thing here will just be z1 squared minus z squared. And at the numerator, you just have 2z. And so at the end of the day, what you end up with, it's this quantity here, okay? But you can see that this quantity is exactly, it's more or less exactly what you have here, right? So except for z. So if I put z here and I also divide by z, this quantity here is exactly this quantity here. So let me actually substitute it here. So here I have 1/2 integral from minus z to z of omega 0 to of z1. Okay. And now let's make another observation. So let's introduce these two functions. I will take x of z to be z squared over 2 and y of z to be sine of 2 pi z over 2 pi. And you can see that dx, it's just z dz. And this differential form, it vanishes at z equal to 0, which I will call A. And so this residue here, it's just a residue at A. Okay. And another observation is that this function x is actually invariant when you send z to minus z. So this means that there exists an involution, which is z maps to minus z, which, well, basically it exchanges the two sheets of this function, z maps to z squared over 2. And this involution leaves A, which is the 0 of the x invariant. But this minus z here, it appears here in many places. So it appears here and here. So let me substitute it with this sigma. So here I will have just sigma of z and sigma of z here as well. Okay. And well, the last observation is the following. If I introduce omega 0,1 to be y dx, well, in this specific case, when x and y are these two functions, what I get here is exactly z times sine of 2 pi z divided by 2 pi. Yes, dz. Which, except for 2 that I forgot here, is exactly what is appearing here, right? So now I can just remove this term and put this 1 over omega 0,1 of z. Okay. But let me make one last observation, and this is the fact that omega 0,1 in this case, and this is very specific of this case here. This is also equal to omega 0,1 of z minus omega 0,1 of minus z divided by 2. And here, okay, here I just realized that the 2 was actually right. So this term here, I can now substitute it here. As I said, the 2 was actually right. So the correct thing here now is this one. Okay. And so this was a long list of maybe silly observation that led us to this kind of formula. As I said, this is essentially what Bertrand and Nicolas did in 2007, but based on many more examples, not just this specific example here. So in their case, they had way more examples to make all these observations. But the main point here is that they now this formula here has nothing to do with the specific case of hyperbolic surfaces or JT gravity. It's just the formula before when you take x and y to be these two specific functions. And so now I can finally give you the general definition of topological recursion. So topological recursion is based on this concept of spectral curve, which is the data of sigma, a Riemann surface, which is not necessarily compact or connected. And then 3 more data, which is a function x, a 1-form omega 0,1, and a 2-form omega 0,2, satisfying certain properties. So more specifically, x is a function from sigma to c that is meromorphic, and such that dx has finitely many simple zeros that I will call A, and I will call the set of simple zeros with this R. And here simple means that the second derivative is non-vanishing. And so because of that, you can see that there exists an involution that I will call sigma A. And this is defined in a neighborhood of each ramification point A. So sorry, I will call the set of simple zeros of the X the set of ramification points, because you can see them as ramification points for the function X. And so this involution, which you can imagine it to be something like this, it's just near every ramification point, something that exchanges the two sheets of this covering here. This satisfies the following property. It leaves X invariant, it fixes the ramification point, and it's not the identity. And this property is actually uniquely determined in this involution. Okay, so you have this function X, which satisfies this property. And then you have, as part of this data, omega01, which is a meromorphic one form on your Riemann surface sigma. And often, instead of giving omega01, you can just write omega01 as y times dx, where y is part of your initial data. So sometimes you will see a different definition of a spectral curve, where here you have y instead of omega01, but it's equivalent. And sometimes this sigma will actually be given as the set of zeros of an expression, like, I don't know, an algebraic expression relating x and y. And in this case, x and y will just be the two projections from this curve that lives inside C times C. And finally, omega02, it's still part of the data, and it's a symmetric meromorphic 2 form on sigma cross sigma with a double pole along the diagonal. And so once you have all these data here, you can now define a bunch of correlators through the topological recursion formula, which is the following one, which is exactly what I tried to come up here from the specific example of JT. But now this is very generic. You have a generic bunch of data, sigma x, omega01, omega02, and out of this you define these omega GNs with this recursive formula. All right. So and this is the topological recursion formula that specifies to the recursion for these Val-Peterson polynomials or JT correlators when you take x and y to be those specific ones that I gave before. Okay, and so before giving you some more examples, let me mention a couple of properties. So first of all, this omega GNs are symmetric in Z1 up to Zn, and this is really not it's not automatic from this formula, because as you can see, Z2 up to Zn, they actually play a symmetric role in this formula. Right here, you split them in all possible ways, and here they appear in a symmetric way. But Z1, it appears here, and it appears in a way that it's completely different from all the other variables. But nonetheless, the property of these topological recursion correlators is that at the end they are all symmetric in Z1 up to Zn, and you can prove this recursively using their definition. Another property is that all these correlators, they have a very specific pole structure. So one can prove that they are all meromorphic, and the poles are only at the ramification points. And you can also control the order of the poles. The order is always less or equal than 2 times 3g minus 3 plus n plus 2. And they also have no residues. And this 3g minus 3 plus n, it's not a random number. It's actually the dimension of the moduli space of hyperbolic Riemann surfaces. And this is not a coincidence. I will talk about this later. All right, so another property that it's somehow inspired by applications from topological string. It's something called the Latam equation. And this Latam equation says the following. So if you define phi 01 to be a primitive of omega 01. So omega 01, remember, it's a 1,4. You can choose a primitive. It doesn't matter which primitive you choose. But after you do so, these omega GNs are given by 1 over 2g minus 2 plus n times a residue of omega g n plus 1 when you multiply this omega g n plus 1 by this phi 01. And in the spirit of Riemann surfaces, this is the same as saying that if you take this correlator here with the genus G and n plus 1 boundaries. So here you have 1 up to n, and one more boundary here. When you glue to it this phi 01, which is something like a disk, then you get exactly the correlator with the same genus, but one boundary component less because you just glued a disk on it. So this is something called the Latam equation, and thanks to this equation, it actually makes sense to define omega g0, which is often called fg, through this formula when you take n equal to 0. And here I should say something, because so in this topological recursion formula, we need n to be greater or equal to 1, because we need at least one variable to start the recursion. So in this topological recursion formula, you always need n to be greater or equal to 1. But then because of this property here, it makes sense to define omega g0 or fg through the Latam equation. Okay, and again, this only makes sense when g is greater than 2. You can see that when g is equal to 1, there's a problem here, but there's still a way to define f1, and there's also a way to define f0, but let me skip on this. It's not so important. All right. Another property satisfied by this omega GNs is a certain homogeneity property. And this says the following. So imagine you start from a given spectral curve, and now you consider another spectral curve with the same data, but you rescaled omega 01 by a non-zero scalar lambda. And so how do you compute the omega GNs that you compute from this spectral curve and from this spectral curve? The point is that they are essentially the same. So the omega GNs computed from the rescaled spectral curve are just the scalar lambda to the minus 2g minus 2 plus n times the one computed from the non-rescaled one. And this is very easy to see because omega 01, it's only appearing in the topological recursion formula here at the denominator, and you just have to compute how many times it appears in the recursion, and it's precisely 2g minus 2 plus n. Another interesting property satisfied by this topological recursion correlators is something called a deformation equation, which has something to do with Seiberg-Witten theory. And these equations that I will not make this precise, but it's nice to know that they exist. They tell you how this omega GNs change when your spectral curve depends on some parameters. Yeah, so here it's a bit technical, this equation, so I will not talk about this, but it's nice to know that it exists. And one last property that I wanted to mention is the relation between topological recursion and quantization. So here it's also quite technical, but the idea is essentially the following. Imagine that your spectral curve sigma is given by an equation like this, right? So this gives you a curve, because here you should think of this as something living in C times C, where the first one is the one where X lives, and the second one is where Y lives. And X and Y are just the projections to these two factors. So this is your spectral curve, and out of that you can consider something called the wave function, which is defined in this way. So it's just the exponential of a certain let's say topological type expansion of the integral of these omega GNs. And if you remember what I said at the beginning, this in the context of random matrix theory, this is essentially the expectation value of the characteristic polynomial. But this makes sense in this more general context of spectral curves. So the point is that if you define psi to be this gadget here, then one can show that this is the WKB solution of a certain quantization of P. And what I mean by this is that you can quantize P in such a way that, well, if you replace X by the operator of multiplication by X, and if you replace Y by the operator H bar D dx, of course here you have to be precise because you have to explain how you order these operators, but I mean, this is part of the statement. You can always specify this a quantization of P in such a way that this differential operator will annihilate this psi here. Okay, so maybe let me move to some examples. Or maybe this is a good moment to ask if there's any questions so far. So if not, I can maybe try to go through some examples. So the easiest example you can think of is something known as the Airy spectral curve. And this is the case when you take sigma to be C, the complex plane. And remember, X is a map from sigma to C that has whose differential has a finite number of simple zeros. And the easiest possible map that has this property is Z squared, or Z squared over 2 in this case. This has exactly one, dx has exactly one simple zero. And if you take y equal to x and omega 02 to be this specific two differential, remember that omega 02 has to have a double pole along the diagonal of, so something that behaves like this. So if you take this specific spectral curve, then the omega GNs that you can compute out of this, they have a very nice physical interpretation. They are correlation function of something known as 2D topological gravity. So this was studied by Witten in the 90s and by Kontsevich around the same years, who actually connected to a very specific matrix model known as the Kontsevich matrix model. And the reason why this is called airy is essentially related to this fact here, because you can see that in this specific case, so if you take x and y to be these two functions, you can see that well, y and x, they satisfy a very specific equation. So if you take y and you square it and you divide by 2, this is equal to x. So the equation satisfied by x and y is this equation here. So if you take this as your p of x and y, and you quantize it in the sense that you substitute x with multiplication by x, and you substitute y with h bar ddx, then the equation that you get out of this is exactly the airy equation, which explains the name here. There are actually many more connections with the airy function, but the upshot here is that in this specific example, you compute this omega gns in a kind of crazy way, recursively, but when you put them together in this specific way by integrating them and taking the exponential of this topological expansion, you just get the airy function. Another example, which is like the brother of this airy case, is called the Bessel case. Oops, sorry. It's the Bessel case when you take, again, sigma to be just c, you take x to be z squared over 2 again, but you take y to be z to the -1 and omega 0 to be the same. And this is called the Bessel case because, again, when you do this procedure here, you get the Bessel equation. And from the physics point of view, this is related to a matrix model known as the Bresan-Gross-Witten matrix model, which was studied in the 80s in relation to lattice Young-Mills. So another example that we saw before is this Weil-Peterson or JT or SYK. So if you remember, this is the case when sigma is equal to c, x is z squared over 2, and y is this sine function. And again, omega 0,2 is this dz1 dz2 divided by z1 minus z2 squared. So if you take this as your spectral curve, then the omega GNs are, well, some specific correlators in JT or SYK, or if you want, they compute this Weil-Peterson volumes through a Laplace transform. And you can even consider the super version of all of this. So you can consider correlators in super JT gravity or volumes of moduli spaces of super hyperbolic Riemann surfaces. And the correct way of modifying this initial data, this spectral curve, is to take the same data except for y, which instead of being sine is just cosine divided by z. Okay, another fancy example, it's still related to hyperbolic geometry, and it's the counting of hyperbolic geodesics when you take the length to be bounded by a certain L. This is also something known as Mesurvich volumes. And in this case, you have to take the same sigma x and y as in the Weil-Peterson case, but now you change omega 0,2. And you change it by essentially adding this sine cardinal function. So here, sinh of x is sine of x divided by x. And here you can see that you have this t here, which is a parameter, which is essentially the Laplace dual to this L. So you're trying, in this example, you're trying to count geodesics with a fixed bound on the length. And you can do this considering this, let's say, one parameter family of spectral curves depending on this T. And when you take the Laplace transform in T, you get exactly this type of geometric quantities. Other examples are from Hurwitz numbers, where you take X to be log of Z minus Z. So these are counting of covers of the Riemann sphere. They also appear in the context of topological string. You have something related to Pandeve 1, where now sigma is the torus, and X is the Weierstrass function associated to that torus. Y is the derivative of the Weierstrass function, and omega 02 is again constructed from the Weierstrass function in a very specific way. You have examples from a generic matrix model, and the general form of the spectral curve is something like this. So the spectral curve is, as I said at the beginning, determined by the leading order of the spectral density, if you remember. And this is the equation where omega 02 is given in a canonical way. And the last two examples I wanted to mention is Graham-Witten invariance of toric Calabi-Yau threefolds. When you have a toric Calabi-Yau threefold, there's always a construction of something known as the mirror curve. And if you take the mirror curve as your spectral curve, you compute these omega GNs, and these contain all Graham-Witten invariants of the toric Calabi-Yau threefold that you started with. And one last example, which is actually still conjectural, is related to knot theory. So if you take a knot, there's something called the apolynomial character variety associated to it, which is again a curve. And the conjecture is that if you run topological recursion on this apolynomial character variety, you compute these omega GNs. And when you construct this wave function associated to it, this is coincides with the asymptotic expansion of the Jones polynomials when you send the number of colorings to infinity. So here, I mean, the point is that there are many examples where you're trying to compute some interesting physical or geometric objects, and there is you can explicitly construct a spectral curve that it's underlying that problem, and then topological recursion is recursively computing all these invariants that you that are related to that specific problem. All right, so and as I said at the beginning, well, you can either look at topological recursion as a nice way of computing your invariants, but the one point of topological recursion is that it satisfies many properties, and sometimes you can use these properties to say something more about your problem. And so this is the last thing that I wanted to talk about, which is the connection between topological recursion and the moduli space of curves. So in the specific case of SYK or JT, we saw that on the one hand, the correlators of these theories are computed by topological recursion, where the spectral curve is the specific one. But on the other hand, we know that these correlators, they are related to volumes of moduli of hyperbolic Riemann surfaces. And so the question is, well, is this relation more general in the sense that, is it true that every time that every topological recursion correlator is in some sense computing some, let's say, objects related to moduli of hyperbolic Riemann surfaces? And the answer is yes, but you have to be a bit more precise, or let's say you have to modify something. And the first point is that this moduli of hyperbolic surfaces is very specific to JT. More generally, you have to consider something slightly different, which is the moduli space of of complex curves. So I will denote it with MGN. So this is the space parameterizing now complex structures on surfaces of genus G with n mark points. So this is called the modular space of curves, where curves actually means complex curves. So it's again two-dimensional surfaces, but because you are parameterizing complex structures, you can think of them as one-dimensional complex manifolds. So hence the name curves. And the easiest example, one of the easiest examples is the case of M11. So this is the space parameterizing elliptic curves. So elliptic curves is another name for complex complex structures on surfaces of genus 1 with 1 mark point. And this space is equal to the quotient of the upper half plane by SL2C. So the image you should have in mind is something like this. So on the upper half plane, the result of this quotient is this strip here, where you identify this side with this side, and this arc with this arc here. And so every time you take a point here, let's say a tau here, what is the genus 1 curve that you get out of this is just this quotient, which is always a torus, right? So something of genus 1 with 1 mark point, which is the origin of the complex plane, that it's mapped to a certain point on this elliptic curve. Okay, and so here you see, here I'm talking about the modular space of complex structures, but here, like before, I was talking about hyperbolic Riemann surfaces. So what is connection between the two? And this is actually a kind of old result due to Riemann. And this result is saying that the space parameterizing complex structure is the same as the space parameterizing hyperbolic structures. So this is something known as the uniformization theorem. And it's a very deep theorem, but the upshot of this is that every topological invariant that it's associated to the moduli space of hyperbolic metrics can be expressed as a topological invariant on the moduli space parameterizing complex structures. And so in the specific case of the volumes of the moduli space of hyperbolic structures, so this Weil-Peterson volumes, one can show that this is the same as an integral over this different moduli space, the moduli space of complex structures, where you take a cohomology class, which is a very specific combination of something called kappa 1 and something called psi classes. And you know, the boundary length here, they appear as essentially coefficients of this psi class. So here, this, as I said, this kappa 1 and psi 1 up to psi n are some very specific two cohomology classes of degree 2 on the moduli space of curves. And so, for instance, let me briefly say what the definition of this psi classes is. So psi I, it's defined as the first Chern class of a specific line bundle, Li. And Li is the line bundle, is the complex line bundle over MGN, whose fiber over a point on the base. So the fiber of Li over a curve of genus G with n mark points is just the cotangent space to C at the ith mark point. So and here, what I mean by cotangent space, it's really the complex cotangent space. So this definition actually depends on you know, the complex structure that I put on C, and it has nothing to do with hyperbolic geometry. So this quantity here, it's really something that is related to complex geometry, but nonetheless, when you put all these things together in this specific way, magically you're computing something in this hyperbolic world. And so going back to the general picture that I was trying to describe. So in the JT setting, we have this correspondence, and the idea now is that if you want to develop this kind of correspondence, not for the specific case of JT, so when you replace this by something like a general spectral curve, so the correct way, the correct thing that will replace this right-hand side is not just volumes of moduli of hyperbolic Riemann surfaces, but something like intersection numbers on the moduli space, not parameterizing hyperbolic Riemann surfaces, but let's say complex structures. I cannot write anymore. Complex structures on surfaces. And so for the specific case of JT, this equality will be something like this, right? And the main question is, well, can we generalize this to, let's say, a general spectral curve? And the answer is yes. So this is the last thing that I wanted to say. It's this theorem due to Einar and Dunin-Barkowski, Orantan, Shadrin, and Spitz. And this result goes as follows. So imagine you fix S to be a spectral curve. So this is sigma together with X, omega 01 and omega 02. And to simplify a bit the discussion, let me assume that X has only one simple ramification point, A. And because I have a simple ramification point, I can choose a local coordinate that I will denote with this zeta around A in such a way that X of Z minus X of A is just, this quadratic term. And I can do that because I have a ramification point, so the first derivative is 0, and it's simple, so the second derivative is non-vanishing. So I can always do this around the ramification point. And what I'm going to do now is define a bunch of quantities. So the first set of quantities, these are some differentials, this d psi k z. In order to define them, let me first define a function. So this function, psi of z, is defined as follows. So let's take omega 02. That depends on two variables, but let's ignore the second variable. Let's look at it as a form in the first variable. And if we take the derivative with respect to this local coordinate zeta, and we evaluate it at the variable equal to the ramification point A, the result of this is just a one form in the second variable. And when we integrate it, we get a function that I called psi of z. And I define this differential d psi k of z to be the kth derivative of psi with respect to x k times, and then I take the differential of that function. Okay, this seems a bit random, but hang on a minute. So in this way, I define some differentials. All right. Then the second ingredient that I want to define, it's something called a topological field theory. So this is a big name for just a single scalar that I denote with this y0. So this is just a complex number that is defined as the derivative of y with respect to this local coordinate zeta, evaluated at z equal to the ramification point. So this is just a complex number. The third datum that I want to define is something called the translation, which will be a formal power series which starts with u squared. And because of that, I can always write an object like this in this way. I can write this T of u, this formal power series, as u times 1 minus an exponential. And if I and I can collect all the coefficients in the exponential as this Tn. So this is just a fancy way of describing a bunch of numbers. But this T of u is defined as steepest descent integral of omega 0, 1. So what I mean here by steepest descent integral is just, the Laplace method applied to omega 0, 1, which gives you a formal power series in u once you get rid of this square root of 2 pi u, which comes from essentially this Gaussian term. And this term here is designed in such a way that you get rid of the first coefficient of the coefficient of u to the 1. Long story short is you can define a bunch of number from this steepest descent integral that we call T. And then there's another gadget that it's called a rotation, which is now a formal power series that starts with a 1. And this is again a steepest descent integral, but instead of taking omega 0, 1, now you take psi, this function here, times dx. So again, this is a very complicated way of giving you an infinite sequence of numbers that I call Rm. And the result of this theorem is that the omega gns that you compute out of topological recursion from this spectral curve, they are equal to some integrals over the moduli space of curves of a certain homology class omega that depends on this data that I defined here, times psi classes, and I can keep track of the power of this psi class with this differential d psi I. And so how do I define this omega? Well, this is exactly defined in terms of this topological field theory, translation, and rotation. And the definition is the following: you have this scalar y0 to a certain power, which is minus 2g minus 2 plus n. And then you have a cohomology class, which is defined as the exponential of a certain combination of natural cohomology classes on the moduli space of curves, which is this something called kappa classes, this kappa n, with coefficients given by this translation, and then a combination of these psi classes and something else called boundary divisors, times this coefficients Rm given by the rotation. So this may be a bit technical, but the upshot is that if I give you a spectral curve, on the one hand, you can run topological recursion and compute these omega gns. But on the other hand, you can do these crazy computations. You compute these numbers here, and you put them together in this very weird way with these cohomology classes. You can construct this gadget, and when you integrate this against psi classes, keeping track of them with these specific differentials, you get exactly the omega gns that you computed through topological recursion. And this, in some sense, generalizes this JT case, right? This Weil-Peterson case. Well, after taking Laplace transform on both sides, you will have something computed by topological recursion here, and a certain combination of cohomology classes on this other side. Let me conclude by mentioning a couple of things. So, well, first of all, I mean, this theorem is from 2012, I think. And recently there was a bit of interest in this because from Gopakumar and Matseng, and the idea is that this theorem here is a kind of gauge string duality, right? Because on this side you have, let's say in the case of matrix models, you have something that it's gauge theoretic, right? Correlators in matrix models. While on this other side, you have something that is more like string theoretic. You have integrals over the moduli space of Riemann surfaces of some cohomology classes. But as I said, this theorem is much older, and it provided many interesting relations between, some enumerative geometric quantities and expressions for these quantities as integrals over the moduli space of curves. And what I wanted to mention is also essentially motivate why this is called, these omega GMs are called cohomological field theories. So what is field theoretic about this? So the name cohomological field theory, I think it's due to Witten, and the actual definition of these gadgets is due to Kontsevich and Manning. And the idea is that this cohomology classes, these omega GNs, they are somehow a cohomological generalization of 2D topological field theories. And what is this all about? Well, the main point is that at the level of moduli spaces, there are some maps between all these moduli spaces. These are called gluing maps. And so, for example, you can take, let's look at this first line. Let's take something of genus, let's say G-1 with n+2 mark points. Well, if you take these last 2 mark points and you glue them together, you end up with something of genus G and n mark points, because you lost the last 2 mark points by gluing them together, but you also acquired a genus in the process. And another gluing map is when you take 2 different surfaces of, let's say, genus G1 with n1+1 mark points, and a surface of genus G2 with n2+1 mark points, and you glue these last 2 mark points together. So now if you assume that G1 plus G2 was equal to G, and N1 plus N2 was equal to N, then you end up on this moduli space here. And how is this related to these omega GNs? Well, being a cohomological field theory, it means exactly that essentially these classes, they respect these gluing maps, right? So if you take omega GN and you pull it back with respect to this map here, this map Q, then you don't get something random, you get exactly the omega associated to genus G-1 and n+2 mark points. And the same is true for this other gluing map. When you pull it, when you pull back with when you take the pullback with respect to that, you get the tensor product of the 2 cohomology classes corresponding to these 2 moduli spaces. And these 2 properties here, you can think of them essentially as a cohomological version of the locality axiom in the context of topological field theory. And one more reason to believe in this theorem here is that, well, if this map, if these cohomology classes, they satisfy these properties, well, this kind of indices here are exactly the ones appearing in the topological recursion formula. So if you remember, when you try to compute something of genus G with n mark points, you will end up with having to compute something of genus G-1 n+2 mark points, or the way of splitting G and the mark points in all possible ways. So I mean, this is not a proof, but it goes in the direction of this equality is kind of consistent. Well, maybe one thing that I wanted to say is a bit a kind of motivation for these names, which right now it seems a bit random. But the point is that this theorem, this statement can be generalized when you don't have just one simple ramification point, but an arbitrary number. So in this case, when you have more ramification points, you will end up with as many psi functions as the number of ramification points. This scalars here, you don't have just one scalar, but one for each ramification point. And all these numbers, they somehow behave well together to form something known as a topological field theory. And again, when you have more ramification points, this translation, it's not anymore just a formal power series with values in C, but it will have values in vectors labeled by, again, the ramification points. So this translation actually behaves like a vector, and for rotations, instead of having a formal power series with values in C, we'll have values in matrices, where the two indices are given by, again, a choice of two ramification points, one for the function size and one for essentially these local coordinates. So this gives a bit of motivation for the name translations, because you will have something with values in vectors, and rotation because you will have something with values in the space of matrices. And this rotation and translation, they actually behave together actually as rotations and translations on the plane. So this actually gives them name. Okay, so, well, I also prepared some examples, but maybe I already talked too much, so maybe it's better for me to stop here. Yeah, so if you remember, the first example of spectral curves was the airy one, where you take x to be z squared over 2 and y to be z. And if you go through all these computations here, this topological field theory, translation, and rotation, you end up with actually something trivial. You will end up with the element 1 in cohomology. So here, this is 1 in H0 of MGN, which means that this omega Gn computed from this airy spectral curve, they compute only psi classes intersection numbers. And this psi classes intersection numbers, the fact that they are computed recursively, this was essentially the context of Witten's conjecture from the 90s that was proved by Konsevich using matrix model techniques. But if you want this formula here, it gives another way of understanding this relation. A second example is again the one associated to the Val-Peterson volumes, or JT. So here the only thing that you change is this y, that it's now this sine function. And if you compute all these ingredients, this formula here will actually simplify in having all this Rn to be 0 and all this Tm to be 0, except for the one multiplying kappa 1, which will be 2 pi squared. So after some computation, you can see that the omega associated to this specific choice of x and y is just exponential of 2 pi squared kappa 1, which is exactly what appears in the computation of Val-Peterson volumes. So you will end up again with this fact about Val-Peterson volumes and topological recursion on the other side. And the last example is the one of Hurwitz numbers, if you know a bit about that. So in this case, you take x to be log of z minus z and y equal to z. And if you compute all these ingredients, you can see that the cohomological field theory, this cohomology class underlying this spectral curve, it's something known as the dual Hodge class. And the fact that Hurwitz numbers are related to integrals of this Hodge class, it's a very famous result known as the ELSV formula. So again, this theorem here, it's also a way to discover, relation between some enumerative geometric objects and integrals over the moduli space of curves, such as the ELSV formula. And that theorem was used to prove many generalizations of this Hurwitz this ELSV formula for different problems. Okay, that's what I prepared.
Okay, great. Thank you very much.